Imagine a world where machines whisper their woes before they shout. This is the promise of predictive maintenance, a realm where we anticipate and address issues before they even arise. No more catastrophic failures, no more unexpected downtime. Instead, we have a symphony of smooth operation, guided by the power of foresight. In the realm of mechanical engineering, this translates to a shift from reactive to proactive. Instead of fixing things when they break, we strive to prevent the break from ever happening. This approach saves time, reduces costs, and most importantly, ensures safety and reliability. Think of a wind turbine, its blades slicing through the air, generating clean energy. Predictive maintenance allows us to monitor its every vibration, every subtle change in temperature, and predict when a component might fail. This early warning allows for timely intervention, preventing a potentially catastrophic breakdown. The key to unlocking this predictive power lies in the fusion of mechanical engineering with the ever-evolving field of artificial intelligence. AI, with its ability to analyze vast amounts of data and discern patterns invisible to the human eye, becomes the watchful guardian of our mechanical systems. Sensors attached to machines act as our eyes and ears, constantly gathering data on various parameters like temperature, pressure, vibration, and more. This data, a treasure trove of information, is then fed into AI algorithms. These algorithms, much like seasoned detectives, sift through the data, searching for telltale signs, anomalies that might hint at an impending failure. A slight increase in vibration here, a small temperature fluctuation there. These subtle clues, often missed by human observation, are easily detected by the vigilant AI. The world of AI offers a diverse toolkit for predictive maintenance. One such tool is the Bayesian network, a graphical model that represents the probabilistic relationships between various components of a system. Imagine a network of interconnected nodes, each representing a component, with lines between them signifying the influence they have on each other. Another powerful tool is signal processing, which allows us to extract meaningful information from the raw data streams generated by sensors. Just like a musician can discern individual notes in a complex symphony, signal processing helps us identify specific patterns and anomalies within the noise of raw data. Predictive algorithms, the heart of AI-powered predictive maintenance, come in various flavors. Some are like seasoned detectives, meticulously analyzing historical data to identify patterns that precede failures. Others are more like intuitive forecasters, using current data to extrapolate future trends and predict potential issues. Imagine trying to find the perfect combination of ingredients for a delicious dish. You could experiment randomly, or you could use a recipe. In the world of AI, optimization algorithms are our recipes, guiding us towards the best solutions. One such algorithm is CMA-ES, which mimics the process of natural selection to find the optimal set of parameters for a given task. Imagine a population of solutions, each slightly different, competing with each other. The fittest solutions survive and reproduce, passing on their traits to the next generation. Another approach is genetic algorithms, which also draw inspiration from nature. These algorithms treat solutions as chromosomes and use operations like mutation and crossover to create new generations of solutions. Through this iterative process, they evolve towards the optimal solution, much like living organisms adapt to their environment over generations. Section 5. Learning from data. The machine learning take. Machine learning, a powerful subset of AI, takes center stage in predictive maintenance. These algorithms learn from data, identifying patterns and making predictions without explicit programming. Imagine them as apprentices, observing and learning from the vast experience captured in the data. Support vector machines, or SVMs, are like skilled swordsmen drawing boundaries between different classes of data. In the context of predictive maintenance, they can differentiate between normal operating conditions and those indicative of potential failures. Gaussian process regression, or GPR, takes a more probabilistic approach. Instead of drawing hard boundaries, it provides a range of possible predictions, along with their associated uncertainties. Think of it as a weather forecast, providing probabilities of different weather conditions rather than a definitive prediction. Section 6. Time, the unseen dimension in maintenance. Time is a crucial element in predictive maintenance. The data we gather from machines is not static. It evolves over time, telling a story of the machine's health and performance. To unlock the secrets hidden within this temporal data, we turn to time series analysis. Kalman filters are like time-traveling detectives, smoothing out noise and estimating the true state of a system over time. They're particularly useful for systems where measurements are noisy or incomplete, allowing us to extract a clear signal from a sea of data. ARIMA models, on the other hand, are like seasoned statisticians, identifying patterns and trends within time series data. They can detect seasonality, trends, and other recurring patterns, allowing us to forecast future behavior based on past observations. Section 7. Seeing the unseeable. Image recognition in maintenance. The world of maintenance is not limited to numbers and graphs. Images and videos captured by cameras and drones provide a wealth of visual information that can be harnessed for predictive maintenance. This is where computer vision, a field of AI focused on image understanding, comes into play. Convolutional neural networks, or CNNs, inspired by the structure of the human visual cortex, excel at image recognition tasks. They can be trained to detect anomalies in images, such as cracks in infrastructure or defects in manufactured products. Self-supervised learning, a cutting-edge technique, allows AI to learn from unlabeled data. Imagine an AI system that learns to recognize different parts of a machine and their normal operating conditions simply by observing videos of the machine in operation. This ability to learn without explicit labels makes AI even more powerful and versatile in the context of predictive maintenance. Section 8. The future is now. Advanced AI in action. As we venture further into the realm of AI, we encounter even more sophisticated techniques that push the boundaries of predictive maintenance. Zero-shot learning, for instance, allows AI models to recognize and classify objects or events they've never encountered before. Imagine an AI that can identify a new type of fault in a machine simply by understanding its underlying mechanics and operating principles. Federated learning enables multiple AI models to collaboratively learn from decentralized data sets without sharing the raw data itself. This is particularly useful in industries where data privacy is paramount, allowing different companies or organizations to benefit from shared learning without compromising sensitive information. Imagine a network of wind farms, each with its own AI system monitoring its turbines. Through federated learning, these systems can share their learnings, effectively creating a collective intelligence that benefits the entire network. This collaborative learning allows for more robust and accurate predictions, ultimately leading to a more reliable and sustainable energy future. Section 9. Conclusion: towards a future of seamless upkeep. The fusion of AI and mechanical engineering is ushering in a new era of predictive maintenance, one where machines are no longer passive recipients of our commands, but active participants in their own upkeep. This transformative technology has the potential to revolutionize industries, from manufacturing and transportation to energy and healthcare. As we continue to explore the vast possibilities of AI, we move closer to a future where machine failures are not a matter of if, but when they will be predicted and prevented. This future promises increased efficiency, reduced costs, and enhanced safety. A future where machines and humans work together in a harmonious symphony of seamless operation. Subscribe and comment for more videos. Thank you.